Hi everyone. In this lesson we're going to take a look at another comparison test to determine when series converge or diverge. So this one is called the limit comparison test, and you'll find that this one is a lot easier to use than the direct comparison test. So the limit comparison test makes this statement. If you have two sequences AN and BN, which are both positive, and you consider the limit as n goes to infinity of the quotient of the two, an over bn, and if that limit is equal to a number L, which is finite and positive, in other words, if this number L exists and is bigger than 0, then the series will either both converge or they will both diverge. So if one of them converges, so does the other one. Or if one of them diverges, then the other one diverges as well. So they both do the same thing. So let's take a look at a few examples of how we use this, and then we'll take a look at the proof. So let's consider this example. Let's determine the convergence or divergence of this series. So the series n squared over n to the 5th plus 3 times n squared plus 10. So if we consider these terms here, notice that when we use limit comparison, we want to try to determine another series to compare these two. So if we consider our sequence values here, the ANs, you notice that for n sufficiently large, the n to the 5th dominates the denominator. So really these two terms don't really matter after a while. They don't really contribute much. So for n sufficiently large, this sequence is behaving like n squared over n to the 5th, which is 1 over n cubed. So what that tells us is that it gives us the idea that this series is going to converge because it's going to be behaving like the series 1 over n cubed, which converges by the p-series test because the p is 3. But we have to prove that, so we're going to limit compare this one to this. So we will use limit comparison with this series. Alright. So it doesn't really matter which one I choose for my AN and which one I choose for the BN in this case. So we're just going to let this one be the AN and this one be the BN. So if we look at the limit now as n goes to infinity of AN over BN, that's going to be now we're just going to flip this fraction up. So when we flip this up, we're going to be like multiplying this by n cubed over 1 when we flip it up. And we get that this is the limit now. So here's our limit as n goes to infinity of AN over BN. And notice that this, because the two polynomials have the same degree in the top and bottom, my limit is going to be the quotient of the leading coefficients. The leading coefficients in this case are 1 and 1. And so my limit is just going to be 1. And that's what the L is equal to. That's the L that's being referred to in the statement of the limit comparison theorem. And this number is certainly bigger than 0, and it exists. So therefore, these two series, they both do the same thing. They either both converge or they both diverge. Well, we know that this one converges by the p-series test because the p is equal to 3, which is strictly bigger than 1, of course. And so since this converges, this one will also converge. So that we can say, therefore, that converges by limit comparison. Okay, so that's how we use the limit comparison. Let's take a look at another example. Let's determine if this series converges or diverges. So if the limit is the summation from 1 to infinity, root n over 3n plus 1. So we have to decide what to limit comparison this with. Well, let's notice that root n, if we sort of think of throwing away the terms that are dominated by other terms, you notice we can sort of throw away this 1 here because the 3 times n is dominating it. And so this is going to be behaving like root n over 3n, which is going to be, if I simplify this, is going to be 1 over 3 root n, like that. And so this is what we can use to limit comparison our series with. So now we're going to use limit comparison with like that. So if we look at the limit as n goes to infinity, now we have to decide, we'll just once again let these be our an terms, and we'll let these be the bn terms. It honestly doesn't matter, but so we're going to look at the limit as n goes to infinity of the an divided by our bn terms. And flipping this fraction up, what we get is, when we flip it up, it's going to be multiplied by 3 root n over 1. And we end up with, and of course we end up with this limit as being 1 again, and that is our L. The L doesn't always have to be 1. It's just 1 in this case because of what we decided to limit comparison it with. But the important thing is that this 1 is bigger than 0, and it does exist. It's finite. So therefore, both of these series will do the same thing. They'll either both converge or both diverge. Well, looking at the one we decided to do the limit comparison with, notice that this one is, if I pull out the 3, now here, this diverges because the p is 1/2. So it diverges. And so since this series diverges, so will this one, and so therefore we've concluded that so it diverges by the limit comparison test. All right. Just one other thing to note here. Sometimes you won't have this 3. You don't have to have this 3 here if you don't want to. Some people would just look at this term and say, well, I've sort of got root n over n. That's going to be behaving like 1 over root n, ignoring the 3. And so you could have used limit comparison just with this, in which case your L would have come out to be 1/3 instead of 1, and that's okay. It's still bigger than 0 and finite, and we still would have concluded the same thing, that our series down here diverges. And let's take a look at one more example. So let's determine the convergence or divergence of this series. All right. So if we look at this, it looks like we can use a limit comparison here with this. Throwing away the terms that don't matter, let's just limit comparison this to this. So I threw away the n and the 1. You could put a 5 here if you wanted. You don't have to, though. Now this is equal to 1 over n to the 5 halves power, and that's equal to 1 over n to the 3 halves. All right. So that's what we're going to limit comparison this with. So now notice that the summation 1 over n to the 3 halves, that actually does converge because the p is 3 halves, which is bigger than 1. So if our limit comparison is successful here, looks like we're going to be concluding that this converges. So if we use limit comparison here, let's take the look at the limit as n goes to infinity of and simplifying this, flipping this fraction up, I'm going to get now notice the n to the 5 halves. We can actually write that like this. That's going to be the same as this, right? Notice n to the 5 halves is the same as n to the 5th raised to the 1/2 power. And I just write that so that we can write this as see, that way we can write it like that. Now as n goes to infinity, certainly what's inside here, what's underneath the square root, is approaching 1/5. And so our full limit is going to be the square root of 1/5, or 1 over root 5. And that's our L. And this L is certainly bigger than 0, and it does exist. So therefore, if we look back at the series that we were using to compare our original series to, 1 over n to the 3 halves, we know that this converges by the p-series test because the p is 3 halves, which is bigger than 1. So this series converges, and so therefore our original series right here converges as well. All right, now let's take a look at the proof of the limit comparison test. Now here once again is the statement of the limit comparison test. If we're given two sequences, an and bn's, where the an and bn are both positive, all the terms are positive, and the limit as n goes to infinity of the quotient an over bn equals L, which is positive greater than 0, and exists, is finite, then both series will either converge or they will both diverge. Now that's the same as saying if one of the series converges, then the other one converges also, or if one of the series diverges, then the other series diverges also. So we want to prove this conclusion, that they either both converge or they both diverge, given these assumptions up here. Now, take note that the statement that they either both converge or both diverge is the same as saying these two things. Okay, so it's the same as saying this. If the Bn series converges, then the An series must also converge. And if the An series converges, then the series involving the Bn terms must converge. So the statement over here is the same as saying these two things. Now we're going to prove the first one, and then the second one will be the exact same proof, and so we won't go over that in detail. If we prove number 1, we'll see that it's number 2 is basically just the same thing, and that will conclude the proof of the limit comparison test. So the proof of number 1, to prove this, let's recall the following. Let's recall that when we say the limit This statement means that alright, so limit as n goes to infinity of an over bn equaling L means for every number epsilon greater than 0 that's given to you, you can find a number n such that the absolute value of an over bn minus L is less than epsilon whenever n is chosen larger than capital N. Now this L here, that's not in the numerator here. Let me just move that down here. Looks like that. And also keep in mind that this number n is usually a function of epsilon. So it usually depends on the epsilon. Oftentimes it might be something like 1 divided by epsilon, or 5 divided by epsilon. So it depends on epsilon. The smaller the epsilon is taken, normally the larger this n has to become. And also keep in mind that this quantity right here, this is the same as saying that it's the same as saying an over bn has to be sandwiched between L minus epsilon and L plus epsilon. So as the epsilons are taken smaller and smaller, the an over bn terms are being squeezed closer and closer towards that limiting value L. Now to complete the proof of number 1, what we're going to do is this. We're going to choose epsilon to be a specific value. We're going to assume that the L looks like this. Say L is right here, 0 is over here. We're going to pick the epsilon to be L divided by 2. So notice halfway, half of this distance is L over 2. So that means that this value then would be L minus epsilon. If I pick epsilon to be L over 2, then this would be L minus epsilon, and out here would be L plus epsilon. Okay, so if we pick epsilon to be L divided by 2, then what that means is there is a number n such that for every little n bigger than capital N. Alright, now what we're going to do is, and also note that this is bigger than 0 here. Now what we're going to do is we're going to focus on this part right here. If I multiply the bn's over, then this implies that the an's so we know that all the an terms are bigger than 0 and less than this constant L plus epsilon times bn for n larger than whatever number capital N might be. Maybe it's 1,000 or 1,000,000. It doesn't really matter what it is. We know it exists. Now also note that we're assuming that to prove number 1, we're assuming that the series involving the bn converges. Now if these terms converge, then so does any constant times the bn terms, the series involving any constant times the bn terms. So now thinking of this as being a constant, note that these terms converge because they are actually equal to, I can just factor that L plus epsilon out, and we know that this quantity right here exists. Alright, so we know that this series converges, and we know that the an's are less than L plus epsilon times bn, so therefore the series involving the an's must converge by direct comparison. And that concludes the proof of number 1. Notice we wanted to show that if the Bn series converges, then the An series converges, and that's what we just concluded. We just concluded that the series involving the Ans converge, and we used the direct comparison theorem within the proof of number 1. Now number 2 is proven in the exact same manner, except we consider the quantity Bn over An. Now let me just take note of one thing here related to that. So if we wanted to prove number 2, we would just say this: it's very similar to the proof of part 1 by considering the limit as n goes to infinity of Bn over An. Now that's going to be 1 over L, because if the limit of An over Bn is L, then the limit of the Bn over An will be 1 over L. Well, that's going to be some other number, call it L bar, which is positive also. If L is positive, then so is 1 over L. And now once you have this fact, you can basically then just repeat the proof of part 1, but instead of using L, you would use the number L bar, and the proof is exactly the same. And all of your Ans and Bns down here in this part of the proof would just flip. The Ans would become like the Bns, and the Bns would become like the Ans. And so that concludes the proof of our limit comparison test.